Hi everyone, this is video 1.2.3 and today we're going to look at the molecular view of concentrations, particularly how they change when we manipulate them in certain ways. Okay, so we're going to consider this solution as our starting solution here. It's a copper solution and this is our particulate diagram. And we're going to put this solution in a cuvette, put it in a colorimeter, and run it at 635 nanometers. And when we do that, an absorbance of 0.86 was reported. So our absorbance is 0.86 for this starting solution. Okay, for situation A, suppose water was added so the volume of the solution is doubled, and the picture here is showing you that. So you've doubled the volume of the solution, and you've only added water. So sketch the diagram for what this is going to look like. So basically sketch in the coppers. And then once you're done, check the boxes for what's going to change. Please pause the video, go ahead and predict that. You can do it in pencil or on a separate sheet of paper, and then come back. Okay, so hopefully you've realized that you've only added water, so none of the coppers have gone away. So basically the coppers are just a little bit more spread out in our solution, and our total solution is just going to be more dilute because we just have some more water in there. So what has changed? The moles of copper have not changed. We still have the same amount of copper. The volume of the solution, well, yes, that changed because we added some, so that one should be checked. The concentration of copper has definitely changed. Our concentration has gone down because we have fewer moles of copper per bigger area. So the concentration has changed. So the volume was doubled. Volume doubled. But no copper ions were added. So basically what we can sum it up and say here is the solution was diluted. Solution was diluted. Okay, so if the sample of this new solution is placed in a cuvette and run through a colorimeter, what would be its expected absorbance? What do you think? So if you said it's going to be half of what it was before, you would be right. So you'd look at 0.86, that was the original. This is diluted, so you've doubled the volume, but the copper hasn't changed, so it would be 0.43, which is exactly half of 0.86. 0.43. And that's because the concentration is half the original, so the absorbance should also be half. They have a linear relationship. So concentration is halved, so absorbance would be halved. Okay. Next situation. Suppose half the volume of the original solution was spilled. Sketch the particulate diagram for the resulting solution and again check the boxes. Please pause it and try that. Okay, so we didn't spill just part of the solution. We spilled half the total solution. So if we imagine taking this and just cutting it in half, we have half left. So we should have drawn something like this. So you spilled half the water, you spilled half the copper. So what has changed in this situation? Well, the moles of copper have changed. They've gone down by half. And the volume of the solution has also been halved. The concentration of the copper, however, is exactly the same. Because you have half the copper, you have half the water left. The concentration doesn't change. So since half the overall volume was spilled, overall volume was spilled, the ratio of copper and water is unchanged. Concentration remains the same. If a sample of this new solution is placed in a cuvette and run through a colorimeter, what would be its expected absorbance? So if you run this through a colorimeter and the concentration is the same, it makes sense that our absorbance is going to be the same. And that's definitely true. So you should get a reading of 0.86 because the concentration is the same as the original. Just because you have less, the concentration still isn't changed. So it would be 0.86. The concentration is unchanged. So absorbance is also the same. Okay, situation C. Suppose half of the volume of the original solution was evaporated. Now think about what happens during evaporation. Think about what leaves the solution and what stays. I want you to think about that, pause the video, and make your predictions. Okay, so in evaporation, the only thing that's going to change is the amount of water present. So half of the solution evaporated, that means half the water is gone, but the coppers are left behind. And you might have seen this if you've ever seen something salty or sugary evaporate. It gets, if you evaporate water from a sugar water solution, put a piece of string in it, you can make rock candy because it leaves behind all the sugar, but just the water leaves. So same thing is happening here. Just the water is leaving. So the moles of copper are going to be left behind, so those are unchanged. The volume of the solution, that's going to change. The volume is much lower. And the concentration is going to increase because now you have more copper per the same per less water. So, well, the same amount of copper and less water. So your concentration is going to go up. So only water was evaporated. So the number of copper ions remains the same. Concentration is doubled. Okay, so if you were to put this new solution in a cuvette and run it through a colorimeter, what's going to happen? What's the expected absorbance? Well, if the concentration is doubled, then the absorbance is also doubled. So it would be 1.72, which is exactly double 0.86 of our original there. So it would be 1.72, which is double the original absorbance. This is because the concentration is doubled. Okay, that's the end of this video. Go ahead and jot down your questions, and I will see you next time.